So let's talk limits at infinity. Basically, what is a limit at infinity? Limit at infinity basically just means as x approaches infinity or x approaches negative infinity, how does the function react? That is what limit at infinity means. Just like how a function reacts at a normal number, how does it react when x gets infinitely big in either direction, positive or negative? So let's determine first that what we need in order to solve a limit of infinity is we need to find the horizontal asymptote of a function if b1. So we need to determine it based on a specific formula, but I'm going to explain to you why that formula works. And here is the formula right here, but so determinable if the degree of the function, so basically if the degree of this thing versus this thing, there's some relationship with those degrees that determines our asymptote. So numerator is equal to denominator in degree. You divide leading coefficients. Let me explain to you why that is. So that means that if we just follow that rule blindly, that means that our thing here is 2 over 3 because these both have the same degree, 2, which means we just divide the front. So why is that exactly? So let's create a number for this that would try to represent how this works. Let's say that each point on these things, or each term is a runner in a race. So here is our really poorly drawn start and finish line. Let's just say start line. So if all the runners start at this gate, if you increase x by 1, let's count the terms of just the top thing and count those as our runners. The bottom one will follow extremely closely, but I'm just going to count the top one, the top term. And for now, I'm not going to include the 2 or 3. You'll see why in a minute. So if we increase the x by 1, this increases by 1, this increases by 1. So we have both runners, x squared and x, seated on top of one another as x increases by 1. Now, x will increase by 1 again, where that's equal to 1, which means our gap started out as 0. We're going to keep track of the gap between the two. So that's as x is 1. So now let's see x is 2. That means we're going to have x squared over here we're going to have x squared over here at 4. We're going to have x over here at 2. The gap is now 2. So that means we're going to have a 2 gap between the two. Now let's say when they're at 3, when x is equal to 3. So 3, this one's equal to 9 now. So now our gap is, what is this, 6. So now let's see again. Let's do it one more time. 4, this becomes 16. This gap here is 12. Now we'll go 5. We'll go 5, and we'll go 25. The gap now is 20. Now notice, as x gets bigger and bigger, the gap between these two terms gets wider and wider and wider. As x approaches infinity, the gap between these two things approaches infinity, which means that as far as infinity is concerned, any term that is not the beginning term is completely negligible. So that means we're left with 2x squared or over 3x squared. Now, if you're dividing one thing by the same thing, you just cross them out as 1. That means that as that happens, this function approaches the term 2 over 3, which is what would happen. That would basically just mean we have a function here that looks like this, and I'm going to just say it approaches from the bottom, where this is our line here, 2 over 3. This function gets closer and closer to 2 over 3 as x stretches outwards. So that's basically how that works. That's also probably the cleanest curve I've ever drawn in my life. Driven. Yeah, nice. That's why those front coefficients work like that. So basically, as far as infinity is concerned, the only variables necessary in any rational function are the leading variables. So now let's talk about if the numerator is less than the denominator. We'll just create a function x over x squared plus 1. So that is equal to y over 0 because in essence, we have here a 0x squared, and then every single time we increase this x by infinity. That means no longer are these terms necessary. So now we're just left with a 0x squared over x squared. We're left with just a 0 over 1, which is equal to 0. So that means it approaches 0. Now let's talk about if the numerator is greater than the denominator. It's some function. So we'll say x squared plus 1 over x. If x squared plus 1 over x is some function, you just long divide to find it. Like, literally, you're able to divide this. So you just divide it. You'll find that when you long divide, it'll be x squared divided by x plus 1 over x. So that would be x plus 1 over x. And then this would be your, this here would be your slant asymptote. It would be a line that goes upwards like this from the origin. And then this would be your remainder. So remainder in this case is not very helpful. But all that means is that as this function progresses, you'll see something like this, and then something like this, or something along that line. Something close to that, which basically just means because this is still approaching infinity that way, that means this is also still approaching infinity that way. Likely when your numerator is greater than your denominator, it will be still approaching infinity. There will be no cutoff because the actual function that creates the asymptote, it has no cutoff. So yeah. Now, let's start with the problems. Now that we understand that the horizontal asymptote is the key to success, the first problem is limit as x approaches infinity is equal to 4x squared minus x plus 4 over 5x squared plus 5x minus 8. Let's just do our runner's thing. As x approaches infinity, all of these terms here become completely negligible and we don't have to care about them. These x's cancel out. We're left with 4 over 5. 4 over 5 is our limit at x approaches infinity because our asymptote is y is equal to 4 over 5, which means it approaches the asymptote. So that's the answer to number 1. These problems are going to go by really quickly. 2, or at least for the most part they will. That's why there's 8 of them. So 2 says, I have a thing here that tells me what it says. Limit as x approaches infinity. It's a horribly drawn infinity. 1 over 2x minus 8. The degree here is less than the degree here. They're not equal, which means this will slowly approach, in comparison to this, 0 over some constant, probably 2 in this case, because 2 is attached to x, which is equal to 0, which means this will approach, as it approaches infinity, it approaches 0, not infinity. I was just thinking about the term infinity. So that is the limit as x approaches infinity for that function. It approaches 0. And now we'll do number 3. I'm just not going to write the number. Actually, you know what? No, because it lets me keep track of where things are when I'm editing in post. This one's a little bit more complicated. Limit as x approaches infinity of 12x cubed minus 5x plus 4 over 1 plus 4x squared plus 5x cubed. I don't like how it organizes it that way, all under a square root. So it looks very complicated. But I promise you, it's not very complicated. So if we think about, in essence, what is this square root doing? It's basically just hitting this entire thing. I'm going to rewrite it so that this cube is in front. 5x cubed plus 4x squared plus 1 over 12x cubed minus 5x plus 4. So it's hitting this entire thing with a 1/2, which means, and I know you can't listen, you cannot normally do this, but because we're dealing with infinite stuff, because we're dealing with how it approaches at infinity, we can take out all of this here nonsense. So that means we go 1/2. We don't need to deal with any of those because x approaches infinity. The gap between every other term gets infinitely big. So now we're left with just this. Now, a radical basically just hits the entire thing with a 1/2, and now we can distribute it because there's no other terms to speak of. So that means this entire thing is 3 over 2, 3 over 2. So that radical is all just kind of a red herring that's supposed to scare you, but it doesn't actually mean much because the degree still stays the same because the radical is being hit by the entire function. So That means it's all still the same. These cancel out. This is our answer because that's the horizontal asymptote, 12 over 5. Oh, I lied. It's not 12 over 5 because you also have to hit this with the radical. So it's actually rad 12 over rad 5, which is also an acceptable answer on a test. On a test, this is an acceptable answer because you don't have to rationalize denominators in the real world. Okay. Now let's go on. Number 4 is, we're going to use radicals again. Limit as x approaches infinity of x plus 4 over rad 9x squared plus 5. Okay, so now let's think about how this one will work. First of all, as x approaches infinity, these other terms approach negligibleness. Let's just think about those first two terms for a minute. As you then hit this with the radical, you're left with x over 3x, which is actually the same. It's the same degree. It doesn't look like the same degree because there's a squared here, but because the radical hits it, then it is the same degree. And then just remember to distribute the radical to that other front coefficient, like I almost forgot to do on the last problem. You're left here with a 1. These things can't, that just made literally a bigger x. I tried to cancel out an x by writing an x and it didn't work. That is just left with a 1 over 3, which is your answer for this one. So don't get confused and think that this is 0 because, oh, numerator is less than denominator. It's not less than the denominator. It's actually the same as the denominator. Okay. Now, 5. Which one is that? I have a paper here that tells me. I just told you that. Okay. Oh, this one's a long problem. Limit x approaches infinity. Horrible infinity signs brought to you by me. Radical x squared plus some constant a of x minus x squared plus some constant b of x. Okay, this one doesn't need to be super difficult. I'll explain to you how this one works. So let's think what the heck is going on here. Limit as x approaches infinity of this nonsense. First of all, we have the runners again. We have a squared term here and a single term here. We have a squared term here and a single term here. These can be, as far as we're concerned, completely negated. The radicals then hit the remainders. We're left with x minus x is equal to the limit. So that means that if x minus x is equal to 0, that means the entire thing is equal to 0. We didn't even have to use a horizontal asymptote rule there. We just had to know that how our runner rule worked. Okay. Now let's go 6. What is it? So limit as x approaches infinity of cosine of x. Okay. What is this one? Because this one's weird. So let's think about, what does the graph of cosine look like really quick? What happens with the graph of cosine? Well, the graph of cosine, first of all, you just have to remember that it's the x value in a circle. So at any given time, the circle x value is starts here and it goes there, and then there, and then there, and then there, and back and forth, and it goes there, and there, back and forth, back and forth. I actually drew a sine graph there because of where I drew my x-axis. So we'll go like this, and then say that that's the axis. Okay? So that would be a really scuffed cosine graph. This thing, going from infinity to infinity, always will oscillate between -1 and 1. That's just how a cosine graph works. It'll just always oscillate between those two, no matter where. So that means that this, as x equals infinity, is actually undefined. It's just undefined because it'll always oscillate between the two. Infinity doesn't tell you where to stop, so you don't know where to stop between -1 and 1. So it's actually undefined. But if you wanted to give an absolute definition answer, you would go -1, comma 1. You could say something along the lines of that. And I don't even know if this would also be acceptable, but I'm sure if you explained a reason why and just said cosine always oscillates between the two, so there's any number between these two would count as the limit. I don't know if that's mathematically true, But I guess you could say that because that's the conclusion I came to when I saw this problem. But for all intents and purposes, when I looked it up, it said undefined. So it's, as far as tests are concerned, undefined. So now let's go. Okay. This is number 6, right? Number 6? No, this is number 7. We just did number 6. Number 7, limit as x approaches infinity, yet again, what a surprise, of rad x. Okay, well, x approaches infinity, well, let's just think about the graph of this. It'll just always go up. It'll always go up. It literally just always goes up. You don't even need to think about the graph. You just know that if you plug in infinity here, it's going to give you infinity regardless of what positive number you set it to up here. And we can also use a limit rule there and basically just say if you're trying to hit a function here with a thing out there, you could just say the entire thing, limit of x approaches 0 or x approaches infinity of x, all under a radical. As you increase x to infinity, obviously this increases to infinity. Increases, nice. So radical of infinity is still infinity. So the entire answer is infinity. So there you go, that's number 7. Now let's talk about number 8, the final problem. Limit as x approaches pi over 2. Oh, different number. Of e tangent, no, not pi, tangent x. Oh, that's a little weird. Why? I don't like that one. I'm not a fan of this one. So let's think for a minute. How does tangent work as you approach pi over 2? Well, it's just, if you don't memorize it, you can just say sine pi over 2 cosine pi over 2 is equal to tan pi over 2. So we go sine pi over 2 is 1, cosine pi over 2 is 0. So this is undefined. So if that's undefined, then how does it change as you get infinitely close or infinitely further away from x over 2? Well, this number stays very, very close to 1, but this number stays very, very close to 0, but isn't 0. So we would actually have this here becoming infinity, because we don't need to know the exact values because we're talking about limits, so it's how something acts as it approaches this number. So if that's equal to infinity, that means this entire thing is equal to infinity. So that's like saying limit of e, or that's like saying, where'd my thing go? That's like saying e to the power of infinity, which just anything to the power of infinity is infinity. So that means the limit is infinity. So that's your answer. So that's how that works. And as you approach tangent from either side of pi over 2, it's still equal to infinity because that's how that works. So that's why you're able to do that. You wouldn't be able to do that if they approach different numbers. You would just be able to say does not exist. But that's how cosine and sine work. So, okay. That is all the problems for 2.6. Okay, done.